basically for people who have a lot of GPUs and they don't find the use of it. Actually, the parallelisms start being useful at the scale of 2 GPUs. So if you manage just to rent 2 GPUs, and I think there are a lot of providers now that offer them at decent prices, you're gonna find this blog useful. So once you have 2 GPUs, you're gonna start asking yourself, okay, should I parallelize over my data? Should I parallelize over Tensor Parallelism, etc.? So yeah, it's not only for big labs, it's actually mostly directed towards community.
It's like, in case people don't know, by the way, like the single price of an H100 is like $2 an hour these days. So 2 is $4. Like it's not super cheap, but it's not like ridiculous anymore. But yeah, Alexa, I interrupted you.
Yeah, it would have been correct if it was like PCA, like reduction, and this plot actually made sense. I like the fact that it's like as you're approaching the kernel, it's becoming like fusion like temperature because you're maxing out the MFUs, so like the temperature is increasing. So yeah, I would be surprised if you were to plot like average temperature, I would expect like a drop going towards the end. So that might be an explanation.
Exactly. Exactly how you mentioned it. And yeah, maybe before diving into the blog, I want to first of all like give credits to my amazing co-authors, especially Leandro and Thomas, who helped wrote like most of the blog, and of course the whole team for helping throughout like the experiments and everything. And one other thing that you're gonna find or you're gonna notice while scrolling through the blog, we try to make most of the widgets interactive. So that you get the most fun reading through the blog and for a better reading experience. Cool. So I think we can probably first start with the high-level overview that we presented here. So for people who like just want to get an overview over what we're going to discuss in this blog, I think I'm going to follow exactly the order of this blog post. And so I'm going to probably start with the TLDR, which we tried to summarize here in this cheat sheet. And so for people who are asking themselves, okay, I know how to fine-tune a model. I know how to train a small model. When I want to train a model on multiple GPUs, or when I want to train a big model that doesn't fit in my GPU, what should I pay attention to? Or what are the factors that come into play? And trust me, there are a lot. And when we were making this blog, when I was first learning about this parallelism, it was so hard to find documentation. It was so hard to find even like libraries that explain what they do. Like most libraries, they just keep adding features, cramming features, and they don't really pay attention to how the different features play with each other, which is why you find that a lot of libraries, they have to refactor the entire code base just for it to make sense. And the other thing is that since the pace is going so fast and we keep having new GPUs, new architectures, new models, like the infra team and the training teams need to update the code bases quite often. So to summarize, we try to summarize them in these 3 factors here. So first of all, there is the memory usage. Like if your model or if a training step, because in a training step, there is not just the model, there is, for example, also the optimizer states, there is the gradients, etc. So if the entire training step doesn't fit in memory, then you cannot even train. So when you're gonna parallelize your model, you definitely need to make it fit in your set of GPUs. The second thing is the compute efficiency. And that assumes that your code base is already efficient on a single GPU. For example, when you train a single model when you train a small model that fits in a single GPU, you must ensure that this model fits already in your GPU and that it trains efficiently. Meaning, for example, you don't have a lot of unnecessary transposes, you don't have unnecessary I don't know, CPU, GPU syncs, and stuff like this. Once you assure that your code base is already efficient for single GPU workloads, then you must ensure that this efficiency scales as you scale your number of GPUs. And for that, we're going to explore a lot of techniques, a lot of factors to pay attention to. The third thing is communication overhead. So of course, besides the compute efficiency, once you're going to add more GPUs, you don't want your GPUs to keep waiting for each other's. Ideally, you want your GPUs to be working all the time. Thus, the word brr. We want to make our GPUs keep burring all the time. And so for a summary, I'm not going to go into details because I don't think a lot of people understand this, and this is the goal of this talk, but I'm just gonna explain how to read this cheat sheet. So in this part, we basically explain the strategy we finally came up with and when to use which kind of parallelism. Hopefully by the end of this talk, we can understand the differences. And then in the middle part, we have the parallelization strategies and which factors to pay attention to. So for example, let's say we start with the simplest form of parallelism, which is data parallelism. Which factors does this affect? First, it's going to affect the batch size. Then it's going to reduce the memory consumption. And how? So here you're going to find that, for example, when you scale DP, then assuming you keep the same global batch size, we're going to see that later, you can reduce the micro batch size, and with this you can reduce the memory consumption. Don't worry, we're going to explain the detail later. And then we do this for each form of parallelism so that you can quickly, for example, see that, okay, when I'm going to use TP, I'm going to shard both like the model, the gradients, optimizer states, activations. When I'm going to use context parallelism, it's only activations that are going to be sharded, not the weights. When I'm going to use expert parallelism, it's only experts, not the entire model. So this is for memory, and then the same for compute. Yeah, compute, it's assuming that we use the 6, basically, as we're going to see later as well. We define compute as 6 times number of parameters times number of tokens that we use. So either when you reduce the number of tokens being processed, for example, when you use DP, or when you're going to shard your model, of course, you're going to reduce the compute processed by each GPU. And then there is communication. And for communication, you're going to notice that some parallelisms do much more communications than others. For example, for TP, you have 4 times the number of layers in the forward, all gather, and in the backward, reduce scatter. Whereas, for example, for DP, you only have 1 all reduce in your entire training step. So just like looking at this, and for example, if you use PP, it's only in the grid, like you only do in the forward 1 receive and 1 send in the forward, and it's times the number of gradient accumulation steps, as we're going to define later. So you can quickly see which which parallelisms do how many number of collectives or how many numbers of distributed operations in a single training step. And then the most important factor in parallelism, which is the compute communication overlap, which basically says how much can you hide this communication under the compute. So that, for example, while your GPUs are communicating activations or they're communicating the model parameters, they can do the compute at the same time. This way, even if you scale the number of GPUs, it doesn't make your GPUs idle, which is the best scenario we can have. And we try to come up with formulas that are explained in the appendix of the blog. I don't know if I made this clear enough, but of course for the... Yeah, sorry?
So actually, yeah, like I had a few questions. Like at least like for all those formulas, were these like analytically derived? Like did you write math, or it's like you experimentally observe these effects and then try to fit a curve?
Exactly. Yeah, it's doing math analytically derived.
Okay.
For example.
These are mostly simple approximations on top of the exact math, and works out roughly like this.
Exactly.
And so speaking of, I guess like one of the questions from Jowney in chat is like, I don't think you sort of cover it quite yet, but I'm curious about the answer, which is like at least at least for anything that related to MFU computations, do you sort of do it differently for MOEs versus like regular dense models?
Yeah, we don't treat that part for expert parallelism. Like MFU, we don't actually use it that much because in the end, it depends on how people define it. So for most of the graphs, we only show tokens per second per GPU to avoid the confusion and the confusion of the reader.
Yeah, like I had trouble defining MFU for a situation like FP8, where like some layers are in FP8, some are like in BF16, and you're like, well, like what is the max? Is it like everything's in FP8? But that's not what people. And it's kind of, it was just broke my brain a bit.
Yeah.
Well, I guess the right way would be to see if an operation is in FP8, then you're looking at FP8 top flops, and then for BF16 similarly, I would expect that makes sense. Although I'm not sure if there is any switching costs like on the hardware level.
But
so you would share two metrics, really?
Sorry.
So you would share two metrics basically, like one for like the max BF16, one for the max like FP8, for example.
Yeah, I would see the amount of computation that happens in a layer, and then if that layer, if the computation happened in FP8, then just like divide the whatever is the maximum with the computation they achieved to get the local. You can have like the local MFU, and then aggregate that across the whole model to get the final number. But that's a great question. I don't know what people do in practice. Usually people just assume it's the same precision.
Generally, yes. Yeah.
Yep.
Yeah. The other thing is like this problem isn't just showed with like FP8. Like even with the operation of flash attention, there was already some questions on how to calculate MFU, how to calculate flops, etc. So yeah, it depends mainly on like the standard way of doing it, which is how papers like agreed on doing it, but it doesn't actually reflect, which is why we had HFU, hardware flops, but nowadays people don't talk about it anymore. Like they switched back to MFU. So in the end, just for the sake of the simplicity of the block, we just went for tokens per second per GPU. And we don't really try to estimate how much MFU you're going to get, just like from DP and stuff, because it depends on so many factors that we try to explain throughout the block.
So Anastasia Filipova is asking sort of a similar question from the previous discussions, which is like, did you find that your analytical formulas overlapped with your empirical results?
Yes, for some of we didn't try all the possible like scalings, but yes, some of them we tried, and yes, they do agree. But as I don't know if we're gonna have time to reach the appendix, but hopefully, if we do, basically they come from like straightforward ideas. Like I think by the end we're all gonna agree that these are true with the assumptions that we're gonna make of course, while calculating them. But these I mean, all of the material just gives an idea on like how to treat parallelism and scaling. But of course, as we evolve, as architectures evolve, as GPUs evolve, definitely there are going to be more architectures, more like tricks, like FP8, like more precisions. And like we don't expect these things to stay true all the time. For example, a very small example, I think that soon people are going to make distinctions between internode and intranode. We're going to have more control over like if communications or how we treat intranode versus internode communications. But as implemented in Nanotron, we didn't have the APIs for that because we were mainly based on PyTorch and transformers, so as simple as possible. But I think that these are coming soon. And so people can include this in the future formulas.
So I also see Samsa in chat. I think Samsa's like a prime intellect, works on a lot of the stuff. So his question is, on the 512 to 1024 GPU scale, do we really need full 3D parallelism, or would simple FSTP2 be sufficient to have correct perf and make the code base very simple?
At the 512 GPU, do we really need to do 3D parallelism? No. So at the above 512, you can only use 2D parallelism, so like TP and DP. So basically, the assumption is that DP starts becoming bad once you move past the 512 GPU threshold, and so you must combine it with another form of parallelism. It can be TP, it can be CP, it can be EP, or anything else. But the idea is that once you reach like a big scale, and that scale depends on your network and stuff. Here we took 512, just depending on our infrastructure. But basically, once you start noticing that DP like starts reaching the limit in overlapping compute and communication, then you must start thinking about combining it with another form. And the other form, it depends on your case, whether you use MOE, whether you use whether you have big sequence lengths, etc.
I think one interesting thing to add to the booklet would be the exact networking configurations you guys had, in the sense, is it like FAT3? How do the spine like switches connect with the leaf switches? All those details do impact what's the optimal strategy, and when do you see the kind of the performance degradation? That would be an interesting section.
Exactly. I mean, we're planning to like share all the logs, all the configs. It's just that if we share the raw things, I don't think that people are going to find them useful. But we're trying to like share them in an organized way. It just takes some more work, but hopefully that's going to come soon. The other thing is, even if we, let's say, share the best configuration we found, it's definitely going to be dependent on our cluster in the current state. Like even throughout the experiment, we made some fixes both to Nanotron library and to our infra that made some throughput changes. So like it depends on a lot of things. I think people shouldn't take these numbers as like the ground truth. Instead, they should understand the logic behind it and try to apply it or find their own numbers for their own use cases, whether it's 2 GPUs, whether it's 1,000 GPUs. Cool. So yeah, maybe I'm going to go quickly to the glossary. So yeah, the glossary just explains the terms used in this cheat sheet and the formulas we used to estimate the peak memory. We're going to see that later, and the compute. Yeah.
So now we have a lot of questions. So I'm just going to go through them one by one. Okay. Wow. They just keep coming.
And
yeah.
We also have like 5 parallelisms I'd like to explore. So yeah, maybe like we take one question and then we're gonna make breaks between the different sections.
Okay. So maybe I will batch this question, which is like, the general question I see is like, what is the impact of like the optimizer on these techniques? Like, for example, if you're using something like Dilico and Distro, like this doesn't all reduce every 40 minutes. Similarly, if you're using a second order optimizer like Nouamane or Shampoo, my understanding of those, like they have much higher memory constraints. So how does your napkin math change at this point as well?
Exactly. It's all about trade-offs. So there is no clear answer. It depends on your network. It depends on how your architecture is. It depends on how simple the implementation is, because not all the open source implementations are perfect. Like even some basic assumptions that we made throughout this blog. For example, we assume that the compute and the computation are perfect, but in fact, they are not, as we're going to see later. Like once you do the overlap, you're going to have an SM, which is a stream multiprocessor, which is consumed by the communication. So that affects your computation. So like these questions, they don't have like a straight ahead answer, but the idea is just to understand the trade-offs that you're going to make. So for example, for like this blog, we used what most people use, like ADEM in 32 precision, FP32 precision, which means that, so the moments are going to be in FP32, and the communication, for example, if you use 0, 1, or any form of 0, you're going to need to, no, you don't need to, you're going to shard them, so you're going to gain memory. So yeah, basically these things. And for example, if you use DLOCO or something, yes, you don't need to sync in every training step, but that also affects conversions a bit. So yeah, there are some questions like this, but there are definitely a lot of things to try out, and which is the goal of this blog, because there is a lot of experiments to be made, and we hope that this blog is going to be a first step for people to start thinking about these problems.
All right, so if I didn't read your question, it doesn't mean I ignored it. It just means I will batch it until we finish this section. So please keep asking your questions and just be patient with us, because we do have a 3-hour talk. We don't want to make it 6 hours.
Optimizing for Mark is optimizing for throughput here.
Okay, so yeah, maybe I'm gonna quickly go over this final widgets. So this one is the memory usage breakdown. So first of all, you need to understand, once you train a model, where does the memory usage come from? Why do you get out of memory error? What are the parts in your training step that takes most memory? For this, we have this very cool widget where you can play with the different configuration, and you can see how, for example, the activation memory changes, each layer, how much it takes, the loss, optimizer steps, etc. And the second tool we made, it's this one. So predict memory, and this is specific for the Nanotron implementation. So if you use another library, you're gonna find another memory consumption, but the idea stays the same. So for example, how do you use this? You can go to any model you want. So for example, here, I go to Llama 3 70 billion. You can copy the config, and you paste it in this tool, calculate memory from config, and hopefully you're gonna find the number of parameters here, 70 billion, the architecture, the parallelism use, etc., and the OOM prediction, which was very nice because like after we finished like a lot of experiments, we tried to see how much we can predict OOMs thanks to this tool, and we found out that we can predict with a 95% accuracy the OOMs, which would be very cool. Like instead of trying a bunch of configuration and see if they OOM or no, we just made a tool to predict OOMs. And of course, it's shared publicly so that you also can like avoid trying parallelisms that are definitely going to OOM. And then, of course, so this model, 70 billion model, you can see here that, so this is the memory timeline. So at the beginning, you're only going to initialize the model. So for this, you're gonna need 140 gigabytes almost, because the model is 70 billion and it's half precision. So each parameter is going to take 2 bytes. So multiplied by 2, we're gonna have 140 gigabytes for the model in it. And then once you do the gradient accumulator, we do gradient accumulator in FP32 for both the parameters and the gradients. Again, there are some libraries that don't store the FP32 gradients. In Nanotron, we do, because we found that it increases stability in our trainings. And then there is the forward-backward peak, the first one. Then there is the first optimizer step. And then there is the second forward and backward. And this one is the peak throughout the training, because after this one, you're gonna keep having these 2 peaks, like second optimizer step, then the third forward backward is going to be similar to this one. So this one is the highest peak you're gonna have in a training step, and it's equal to these different parts. So it's cool to see like which components take the most memory, and to like estimate whether you're gonna OOM or not. And yeah, quick. So for people who are wondering, how do we do the OOM prediction? We just like calculate the second forward backward peak, and if it's above 75, I think, jigs, it OOMs from our experience. Because we use H100s and they have 80 gigs of memory. I hope that this was clear. And then the second tool we had, so first of all, there is the memory viz. Okay, so there is the original memory viz by PyTorch team, a very, very cool tool that I don't know if it has the praise it deserves, but it was very useful for me to understand where the memory consumption comes from. Let me quickly pull up.
So maybe I can give the quick history around this tool. So this tool was built by Zachary DeVito, who built the CUDA caching allocator in PyTorch. And indeed, it's one of the tools that like has helped us debug the most memory issues. If you're interested, Jane Shu has like some really interesting talks online around slaying ooms where she uses this extensively. But yeah, I think this is a very, very underrated tool. I 100% agree.
I agree. So this tool, yeah, and I don't have to go into details, but is this the best one to see? Yeah. Okay, so this is, for example, with DP1, TP8, PP1, and we're gonna see what those means later. But basically, different form of strategies. We accumulate 3 times. So this is the gradient accumulation steps. Micro batch size 8, 0, 1, etc. So since we accumulate 3 times, so the first forward backward is this one, and then we're gonna initialize our optimizer. This is probably not the most straightforward thing, but the idea is that you can see like at any point of time what's taking up memory in your training step, and you can even identify the exact line code that allocated it, which is really cool. And then the other cool thing is this allocator state history, where you can just have fun looking at the memory allocation throughout your training step and see at which time there are some parts that are being reserved and some parts that are being freed, etc. And which also make you ask some questions about the CUDA allocator, the CUDA caching allocator. Like some decisions are not ideal, but it does the job. And otherwise, we also made like another, basically just built on top of it to add some very small features that we hopefully can add to the original tool. So here, for example, we once, I think this one was too big for it because it doesn't work on the local space. Let me take a smaller one. Oh. Anyway, otherwise we just implemented like the sorting mechanism so that you can sort by the number or by the size of this operation, and you can also filter by the operation. So for example, for me, I could filter by the allocation, and I could only like see the allocation things, and sort by the sizes so that I can automatically jump into the step that allocates the most memory and see where that comes from. And that helped me understand the fragmentation issues in the Nanotron code base. I hope that was clear. I don't know if I can show this, otherwise you can just play with it later on. Yeah, cool, it works here. Yeah, maybe the detail by default should be reduced a bit. Cool. So these are 2 tools we developed to understand the memory, to solve the first constraint that we talked about, which is, first of all, the model should fit in the number of GPUs you have. And for this, you should be really careful about the memory management in your tool. Because as you can see, like even some buffers for communication can end up taking most of your memory. And without further ado, maybe we can tackle quickly the first step. So the first step is simply training on a single GPU. It lays down the basics. So there is a model, you do a forward, backward. In the backward, you're gonna compute the gradients. And using these gradients, you're gonna do the optimization step, where you're gonna first of all allocate the optimizer moments, and then you're gonna update your original model. For this, we're gonna use some batch size formula. So as you can see here, okay, here probably not the best one, but we're gonna use basically BST, which is batch size in number of tokens, when we're gonna talk about the batch size times the sequence length. Otherwise, batch size is just the number of samples. And as we explain here, in the literature and the currently trained LLMs, a good batch size, or later I'm gonna call it global batch size, when I'm gonna have multiple GPUs. So the final batch size should be around 4 million token, or it ranges from 1 million or from 4 million to 60 million, depending on the size of the model, etc. And that's also a limitation, because as we're gonna see later, some forms of parallelisms, they need to scale the number of tokens or the number of samples each GPUs will see, because some forms of parallelism, they partition the data, and so you can't just scale them infinitely. For example, DP, you can just put 1 million GPUs on DP. Otherwise, you're gonna end up with 1 million samples seen by each GPU times the micro batch size. And then we put some like small, this is what we've seen earlier, like the memory profile for the first training steps is the same one as we explained later. You can also see here, like when the forward happens, when the backward happens, and when is the optimizer state, the optimizer step. A basic formula on how to calculate the number of parameters. Yeah, I'm gonna go quickly through these because I don't have time to go through everything. So basically, if we assume that n is the number of parameters, and this is what you hear about, like, I don't know, a llama that is a 70 billion number of parameter. So what does that entail, like from a memory standpoint? So to find the memory usage, you're gonna multiply it by 2 to find the equivalent in bytes. So for example, if you have n number of parameters, 70 billion, you're gonna multiply it by 2 to find 140 gigs. And this is the memory used by the parameters. And then it's the same for the gradients, because for each parameter, you're gonna need a gradient. And if you store the parameters in FP32, you're gonna need the double of that, because these parameters are in half precision. You're gonna need to store the equivalent in full precision. And then there's the optimizer states. For in this blog, we use Adam, as I said, in FP32. So you're gonna have 2 moments. Each moment is in FP32, and it also requires 4n plus 4n. So you end up with this size needed in a training step. And these are some numbers into how much memory does each model need. And you can see that it quickly scales very fast. And so if you want to train a model of this size, you're gonna definitely need to parallelize over multiple GPUs. Is it?
I mean, probably worth mentioning that you can always offload, but this is to make it reasonably fast and to have reasonable MFU. You wanna start parallelizing. Otherwise, you can just use SSD like or host RAM memory, but that's like not fun because then the GPUs are not going burp.
Absolutely. So yeah, exactly. Offload is one of the strategies. We're gonna also see activation recomputation and gradient accumulation, which is also two other strategies to solve this problem. So this is our first problem, and I noticed that I should probably go faster than this, otherwise we're not gonna finish.
Yeah, we're at 1/8 of the talk, so the scale will be done, in about 8 hours.
Basically, sorry. Okay, let me go then probably faster through this. So activation memory, this is taken from this paper or this blog that explains how it was calculated, and we're gonna see later details onto how it was calculated. Basically, when you train a model, when you do the forward, you need to store activations to use them in the backward, right? So one simple idea would be, probably I don't need to store them, right? Let's just store some activations, for example, between layers or at some points of time. Or for example, I'm gonna, instead of storing the activation between every operation, I'm just gonna store it between 2 or 3 operations. And when I'm gonna do the backward, I'm just gonna, for example, in here, I'm just gonna reuse the activation stored here, and I'm gonna do a small forward and then do a backward. Why is this necessary? Well, this would allow me to not store all the activations here. And we found that there are some, as found by this paper, we found that storing or some activations are very big, and just by like saving or by checkpointing, there are multiple names for this technique. Some people call it activation or computation. Some people call it activation, checkpointing, etc. It's the same thing. So basically, by saving this by not saving all the activation, thus by recomputing some activation, we can achieve 70% activation memory reduction at a 2.7% compute cost, which is nothing. And this is what most libraries do. Selective recomputation, I think all of the distributed libraries use it now, and it's even now part of flash attention, so it's done under the hood.
Do you know which activations are recomputed in Nanotron in particular?
Yeah, so we support all modes. We even have a decorator that you can add to any part of your code so that you recompute only that part. But I know, and this was, okay, so Nanotron, we started development 2 years ago or even more. So yeah, it started around 2 years. And at the time, I know that now there are even better APIs in PyTorch to do recomputation. So I don't think, so you can control what activations to recompute.
So at least within PyTorch, it's a hard-coded list you can grep for. The 3 ones I remember the most was linear, attention, and conv were the ones that you never recompute. And so otherwise, yeah, it's fair game.
Yeah. There's also the checkpoint method that you can apply to anything you want. And then, yeah, we have here some example onto. So you can see here just from without recomputation to selective recomputation, how much memory you're saving. So that is crazy. So that was the first method to save memory. The second method to do it is using gradient accumulation. So let's say you want to train using, I don't know, 16 batch size. But of course, the bigger batch you have, the more memory you're going to need. So instead of doing a forward pass and a backward pass with the entire batch size, you can divide it into micro batches, which is the idea of, and then do this sequentially, which is the idea of gradient accumulation. You do forward, backward, and you store the gradients, and then you do another forward, backward with different inputs, and then you do forward, backward with different inputs. Each time you're gonna sum up the gradients, and at the end, you're gonna do the optimization step with the sum of the gradients, which would be equivalent to having the same global batch size. So of course, here we're gonna trade off memory. So we're gonna gain memory, of course, and we're gonna reduce memory, I mean, but at the cost of more compute. So this is the first trade-off we noticed, that you can always like reduce memory. Let's say you're in a very critical use case where you have, for example, only 2 GPUs or 3 GPUs, but a very big model that you want to train. So you can always do like more compute to save memory. But of course, at a certain point, the cost outweighs the benefit, so it doesn't become interesting anymore. And before concluding this first step, we talk about the final tool we're gonna talk about, which is the profiling of GPU compute and communication, thanks to the amazing profiler tool by PyTorch. So this is the snippet you can use to generate this trace. And looking quickly at this trace, basically, you're gonna see this thread, which is the CPU operations being made. This thread handles the CPU in the backward. And in these streams, this is where the GPU does the work. So you're gonna have multiple streams. And for example, I think it's always stream 7 that handles the GPU computation. And you're going to have other streams that handle GPU communications. But of course, you can always control the CUDA streams in your code base, so you can have more than these streams. The idea is that, so when you're going to run PyTorch code, so your CPU starts reading your code base, and then when you reach operations like matrix multiplication, or I don't know, transpose or dot copy or something, so the CPU is gonna launch a kernel that's gonna be run in your GPU. And that operation is done asynchronously. As you can see, these operations, they are read by the CPU here, and then they are scheduled here. So they come up later in the GPU, which makes the like GPU and CPU run asynchronously. And the other thing to pay attention to is the communication and the computation. So for example, you can see here that communication and computation are happening almost at the same place. We should zoom in to see if they are really overlapped, but generally they seem to be overlapped. But here you can clearly see that there is no computation happening while this big order reduce is happening. And this is the bad scenarios that we want to avoid at all costs while doing parallelism. So this is a very cool tool that you can use to understand if your GPU is going burr or if it's being idle while it's doing communication. And I think we can take a small break to take some 2 questions before moving to the first form of parallelism, which is data parallelism.
All right, so I guess like one of the questions I noticed in chat was like Joe Al-Khouri asking about, are you interested in extending beyond GPU memory entirely? Like, have you sort of investigated things like zero infinity with CPU or NVMe offloading, especially in GPU? I think we talked about it briefly, but maybe we can elaborate more on this now.
Sure. So yeah, another technique that we didn't mention in this blog is that we can always offload to other disks. So it can be either other memories, sorry. So it can be either be the CPU RAM or the disk. Like the worst case, you can even like store your activations in the disk or store your optimizer states in the disk. And then you only load what you need when you need it. So this is like at a very, very extreme cases. But as we know, and as we're going to see later, the biggest bottlenecks are the data movement. You want to diminish data movement at all costs. So if we later we're going to talk about the GPU communication internode, which means like in a single DGX node, for example, or that was intranode or internode between multiple nodes. And we're gonna see 2 different networks. So there is NVLink, which is very fast between multiple GPUs, and there's the network, which is multiple nodes being connected with InfiniBand, for example, or EFA, etc. And just EFA, which is already optimized, it's very bad. But then when we talk about moving data between GPU and CPU or CPU and disk, it's even like slower, which is why these techniques come at very extreme cases, usually, unless they are overlapped correctly. As we are going to see, for example, 0.3 is one example that we're going to talk about, and that can be extended to 0 infinity, which is CPU offload, anything else.
The second question, I'm going to batch those questions because they're both by Calvin E. Young, which is like Yifeng, sorry, which is, did you guys face any reliability issues at 1 GPU scale? And basically also asking about like what kind of comms did you use within all your nodes? Was it NVLink? Was it something else? So yeah, like where was your cluster basically?
So for the reliability on a single GPU, yes, maybe I can show quickly. Yeah, you can see that. So here I'm plotting the average that each collective takes, starting from a single node to multiple nodes. And also plotting the 5th and 95th percentile ranges. We can see that at single node, we get like correct throughput, but once you move to multiple nodes, you're gonna have a bigger variance.
So Nouamane, I think the question was less about the performance degradation, more about reliability in the sense of like, did you have to do any node hot swapping or stuff when the actual hardware like fails and which obviously with more nodes, given that every single node has some reliability rate, failure rate, then as you scale up, like every 30 minutes or something, you might end up having some type of like either networking issue or GPU ECC errors or whatever.
I see.
Any comments on that?
Yes. So in our infra, we use Slurm. Since we're only running benchmarks, each benchmark is run on 3 iteration steps. It's not like in the same setup as training, where you don't want the training to stop, and so you need to swap nodes. So in our case, it was just like short benchmarks of 3 iteration steps. So either the benchmark succeeds or it fails. And yeah, if it fails, you're just gonna run. So the second job in line kicks in, and Slurm like takes care of that.
So wait, if I understood you correctly, you were never running longer runs, like you were just doing a few steps always, right? Is that correct?
Yeah. So yeah, even just with these benchmarks, it took a couple months. if we plan to do longer runs, it would have taken.
Interesting, because like you had what, like you mentioned 4,000, but you filtered out like maybe 8,000 or more. So like, but if you're running only 3 steps, does that really take that many months, or was it?
Yeah, good question. I don't know if you included it at the blog at some point, but yeah, a lot of content didn't make it to the blog. It was actually much bigger than this, but I think it was near the end. So in the lessons learned, and we're thinking on adding that part because it's basically the lessons we learned. So for like few steps, ideally each training step should have taken 2 minutes or like 3 minutes. Assuming that just Slurm running a job takes like 30 seconds or 40 seconds in our case. But we found out that because of the node failures, because of some infra issues that we had to fix, some jobs took like 2 hours, imagine. So there was a variance between 2 minutes and 2 hours for some jobs. And so we had to come up with strategies for these cases. And also, since we were basically cramming a lot of configurations, we started noticing that some configurations created some issues in specific cases. But yeah, we'll try to document all of this later, but it's definitely some very interesting findings in infra in that case.
Yeah, I think this would be an interesting orthogonal block to this one, where it would take just one configuration at 512 GPU scale or 1024, and then run temporally, see the types of issues you encounter. And I think the Imbue folks a few months ago basically described their whole process building up their cluster from scratch and all of the various issues they were encountering. And I think like that type of reliability blog post is missing currently other than InView is probably the closest that matches what I have in mind.
Absolutely. And I think there's also in the Llama paper, the Llama 3 paper, they talked about some lessons learned from their infra, and I found it to be a very good source of information. Basically, they tried to count how many issues or how many types of issues they ran into throughout their Llama 3 training. And it was very interesting because while doing these benchmarks ourselves, we sometimes run into the same issues as them. And we also, our infra team also developed some tools to monitor GPUs better, to reduce the restart time and stuff like that. So it was a very cool lesson for us as well. And yeah, our infra team is also working on open sourcing these tools so that anyone with a cluster will benefit from it.
All right. I hope everyone enjoyed the quick break. I think with that, let's go to data parallelism.
Yeah, and so since there is 5 parallelism, I'm gonna try to make it as efficient as possible. So yeah, so the idea before was that, or the idea behind data parallelism, and I think this is the form that most people are familiar with. It's basically the class DDP that you call in PyTorch. So what does this entail is that before we've seen that in gradient accumulation, in each forward-backward, you're going to see a different, what we call micro batch, or you're going to see different samples. And then you do that sequentially. Give me a second. Let me just...
One-third of the way there, the alarm, reminding himself.
Yeah, exactly.
Right. So yeah, as I said, we had to do that sequentially in the gradient accumulation. So the first idea would be, since now we have 2 GPUs, why don't we parallelize this operation? And so each GPU is gonna see a different chunk of data or different batch, and do that in parallel. And then we're gonna sum up the gradients between multiple GPUs. So I think this is straightforward. So what does this entail? So for example, in the forward, this is the GPU computation stream, the GPU communication stream. And what's cool is that we tried throughout the different forms of parallelisms, we try to keep schemas like this that show when is computation overlapped with communication and when do the communications occur. And this is also in a similar way as the torch profiler. So you're going to have stream for GPU computation and the stream for GPU communication. But then I think later we're going to have even for NVLink communication. But yeah, I think this is going to come in the future. So for now to understand, let's say our model has 3 layers or 3 components. So the forward is going to go through layer 0, layer 1, layer 2. Then the backward is in the opposite way. So it's layer 2, layer 1, layer 0. And then I'm going to have to all reduce all the gradients I made. So for example, here, since, for example, I've seen 3 batches of data, I don't know. So let's say I did multiple forwards, backwards. It depends on the global batch size. After I'm done doing the forward, backwards, my multiple GPUs need to sync their gradients. For this, there is an operation called all reduce. I don't know if I have time to explain the different distributed communications. I think I can quickly find the link for it, or maybe just go here quickly. This is the difference between reduce and reduce. Basically, or reduce is just you have multiple GPUs, you're gonna do a function, which is why it's called reduce. In our case, it was sum, it can be average, or it can be anything you want. And then all of your GPUs are going to have the same output. So this is
It
the
should
first.
be average, though, right? The radius should be average, not some when you're doing data parallelism or whatnot.
Yeah. So yeah, that's also a question. Like some libraries do average, some libraries do sum. I think it's, yeah, I don't remember exactly. Probably it's average, but yeah, I need to double check. Maybe it's average indeed.
I mean,
But
you can always compensate on the loss side. Like you could sum it up, and then you have to divide somewhere. Otherwise,
exactly. Yeah, because I remember that in PP we had to do the same thing with the loss. So yeah, we pick the standard. Sometimes you do the sum in the gradient. Sometimes you compensate for it on the loss side. But the idea is that you try to have the same gradients as if you had no parallelism. So you just need to compensate how you calculate the loss. Cool. But the idea is that, oh, sorry, this is not where we were. The idea is that, so in the gradient accumulation, you have multiple steps done sequentially, and then you do the optimizer step. In this case, each GPU is doing it in parallel, and then you're gonna all reduce between different GPUs, what we call the DP ranks, to sync the gradients. And then you're gonna do the optimizer step, and then you do the forward, and you continue. So here, as you can see, this communication is exposed. What do we mean by it's exposed? It's not overlapped with any computation, which is very bad, a big no. So we definitely need to find a way to overlap this. So the first idea is that we try to overlap this gradient synchronization with the backward pass. And we do that, we do that at the parameter level. So let's say, yeah, so we do the forward of the first layer, second layer, third layer. Backward is in the opposite side. And once I do the first operation, for example, here is going to be the loss calculation, and I start calculating the gradients. Once I calculate gradients, I can already start reducing them while I continue the backward. So I don't need to actually wait for all the gradients before syncing. I can start syncing from the first gradient. And this would enable overlapping this part of the computation with communication. But you can see here that the issue is that you have a lot of communication collectives, and that is very bad. Why? Because of the spaces between these collectives. So each collective is going to come with its own, what we call base latency, its own delay, and which is bad. So the space between these two is basically idle in terms of communication. So ideally, we want to have the fewest number of collectives, which is why we go to our second optimization. Here, you can see that we only do 3 communications or 3 collectives in a training step, of course. So how do we do that? It's what we call the bucketing. The bucketing, sorry. We bucket the gradients. And the idea between bucketing is that instead of all reducing each gradient as it appears, we can wait for some gradients, which what we call a bucket. We can wait for a bucket of gradients to be calculated before communicating it. Here, for example, it's the layers. If we say that we wait for the layers to be computed, that's gonna correspond to a layer, or it can correspond to a size, like a fixed size. For example, when you use DDP by default, I think the default bucket size is 25 megabytes. I don't know if we wrote it here somewhere. Yeah,
I think so as well.
Yeah, I think it's 25. Yeah, it's something like this. This is the argument to control it. And so, for example, one thing you can try is to play with this bucket size to either like wait longer before you start communication, or make it smaller so that you can start communicating earlier. But you can see that it depends on this time and this time. So there is no definitive answer on how to set up the communication size. And then the final optimization is basically combine it with the gradient accumulation so that you can have both like DDP, which means each different GPU is going to see a different batch, and each GPU is going to do gradient accumulation. So instead of seeing the whole batch at the same time, it's gonna see the different batches sequentially. And the final formula becomes this, and I can finally introduce global batch size, so I can start talking about it. So before we only talked about batch size. Now the global batch size is the micro batch size. And throughout this talk, I'm gonna refer micro batch size to the batch size seen by each GPU at a training step, which would make things very easier for people to follow up. And we can use this micro batch size to calculate the memory later on very easily. So this is the micro batch size. There is the gradient accumulation, which is the GAS sometimes, which is the number of gradient accumulation steps, and DP, which is the DP size. So how many GPUs across the DP axis. We're gonna see later on that we're gonna have multiple forms of parallelisms, which means that GPUs are going to be interconnected on different axes. So there are some GPUs that are going to communicate gradients. There are some GPUs that are going to communicate activations, etc. And this is where it gets interesting once we move on to multiple parallelisms. So to summarize our journey up to now, yeah, you can define the best global batch size. You select the sequence length, then you can calculate the global batch. You can define the micro batch size depending on how many GPUs, etc. And then you can set up DP, and then you can set up the gradient accumulation at the last step just to save up more memory. Cool. So how does this translate in our benchmarks? So as we can see, DP is like the parallelism that takes the least number of communication. Why? Because it only communicates the gradients, actually. So everything is fixed, and the gradients can be greatly overlapped with the backward. So you have the entire backward to overlap your gradients. So it's a very nice way to do parallelisms. And we can see here that it scales very well. So this is, for example, the rank or the degree of DP. So for example, 8 means we have 8 GPUs, 16 we have 16 GPUs, and all of them throughout the DP axis, right? So once we move from 8 GPUs to 16 GPUs, we're gonna lose 6% of throughput. And to go back to your questions before, so here we talk about throughput and not MFU to avoid all the confusions.
I think worth mentioning here again is that this is like a big function of the underlying networking, right? Because what is the main bottleneck here? When you're doing goal reduce, you are sending every GPU needs to communicate 2n weights, gradients, and then as you're scaling up, all of those GPUs have to communicate 2n, and so you get to congestion in the network depending on the network design. So I think this is where you could have a complete, like just a single blog post or booklet on networking. And I don't think people, because rarely who has to build cluster or think about these things. Back when I was at DeepMind, most things are really abstracted away from you, so you don't have to think about it. But I think it would be a very interesting topic to understand what goes into design. And I think there's like maybe 2 or 3 families that people usually tend to implement. So it's not that broad of a topic, but it's very interesting.
Exactly. And so so we can see here that we can scale 1632 and without a big loss in performance, up to 256 in our case with our implementation. So it not only depends on the network, it only depends on the implementation. So for our case in Nanotron, we used DDP by PyTorch with the default bucket size. And this is the result we had. And we can see here that the memory usage stays fixed. Why? Because we didn't change the model size. Like DP doesn't shard the model. It doesn't shard the data. Like you always have the same micro batch size. So it does shard the data, but it keeps the same micro batch size, which is why I defined micro batch size as the batch size seen by the GPU at each training step. And so we can see here that the memory usage stays constant as we scale DP. We don't gain, like we don't save up any memory, and the throughput scales nicely. And we can see here that at 256, we already start seeing some bad performance drops, which is why in the cheat sheet we talked about 512, but that's because 03 overlaps a little bit better than DP. And so, yeah. So how does this scale once we scale our model? So for the 1 billion model, so here is the sequence length, or if we want, it's the batch size times the sequence length. So it's just the number of tokens. Basically, once we have bigger micro batch size, we can see that the activations go bigger. But here we can see that once we move from the 1 billion to the 8 billion, the model already doesn't fit. Even with the 1,000 micro batch size, it doesn't fit. And the 70 billion, of course, it doesn't fit on a single GPU. So DP is not enough anymore, which is why a lot of people, when they want to use DDP with big models, doesn't work, although they are actually parallelizing, but they parallelize on the data, not the model. In here, the model itself is too big. So we need another form of parallelism, which is zero. So what is the zero technique? The zero technique appeared with the deep speed, and it has 3 stages. It's nicely explained in this graph. Credits to the authors. So here we can see that we have parameters, gradients, and optimizer states. So the baseline is that every GPU has a replica of everything. So every GPU has a replica of parameters, of gradients, and optimizer states. So the question would be, why can't we shard each of these things? And this is what 0 does. So 01 will try to shard optimizer states. 02 will try to shard both optimizer states and gradients. 03, all of them. And 03 is what other people call FSDP. Mark, throughout the vlog, I'm going to call it 03, but please don't be mad. Just to make the difference between 02 and 01. But 03 and FSDP are essentially the same techniques.
Yeah, I mean, for what it's worth, I learned about distributed programming in the first place from reading the Deep Speed's team's blogs and their docs. So, like, I actually deeply admire Jeff and a lot of the folks there. Yeah, sorry. So please keep going.
Yeah. So 01. So we made here a small visualization to understand what happens. So obviously, when you're gonna have sharded parameters or sharded anything, you're gonna need to communicate them, right? So what do we need to communicate here? So in 01, we said that we're gonna shard the optimizer states, right? So for example, if you use Adam has 2 moments. So each moment is going to be sharded across your GPUs. So what does that mean? When you do the forward pass, the forward pass is the same because each GPU has a copy of the entire model, which is why the parameters here are full. But the optimizer states we said are sharded. When we do the backward, each GPU again has all of the gradients, but since it's DP, you can see they are in different colors because each GPU sees a different micro batch. So since each GPU has a different chart of optimizer states, we don't need all of the gradients. So we're just gonna do a reduce scatter here to only sum up the gradients that are going to be needed later. So I'm gonna explain later the difference between a reduce scatter and all reduce, but the idea is all reduce would sum up all of the gradients in all of the GPUs. So if I had here all reduce, all the GPUs would have the same gradients, which would be the sum of all the gradients. But reduce scatter means I'm not gonna have a copy of all of the gradients. I'm just gonna sum, and each GPU is going to have only a shard of the final output, which is why it's called scatter. And we have, I think it's easier to show graph for everyone to follow. Yeah, and here it explains exactly the difference between the two. But for my case, yeah. So yeah, well, let's focus on the reduce scatter. So I have A, B, C. Before in all reduce, in all reduce, I had A, B, C, so different tensors. And then I'm gonna apply a function on them, which is sum, for example. And I'm gonna have the same output on all of them. So it's the same output on all GPUs. So whereas in reduced scatter, I'm gonna have A, B, C, F is going to be the sum, but every GPU is going to have a shard of the output, which is the difference. And you can read this part later to understand. But, and the idea is that, okay, let me probably explain all gather so that everyone understands this. So all gather means you have different shards in different GPUs. Let's say GPU 1 has A, 2 has B, and 3 has C. All gather is going to combine the different chunks. And at the end, we're going to end up with the same output on all the GPUs. So ABC, ABC, ABC. And so in a way, all reduce is actually the combination between reduce scatter. So that's all the GPUs have a chunk. And then I'm going to do an all gather to combine these chunks. So in that sense, all reduce is actually the combination of reduce scatter and all gather, which means it would take twice the time as all gather and reduce scatter.
I guess the one important thing is like because they're separate, you can essentially overlap computation. Like you sort of make the computation intermediate, and then you can overlap things like differently. So this is one of the main reasons why it's helpful to think about like sort of the comms arithmetic in this way.
Exactly. And so, as I said, since all reduce takes twice the time as reduce scatter, we always try to do reduce scatter instead of all reduce whenever we can. So for example, in this case, as I said, since we don't need the full gradients, I'm not gonna do all reduce, I'm only gonna do reduce scatter. And if you pay attention to the colors, I think you can understand this. And then since I have sharded optimizer steps, I'm only going to update the parameters that correspond to these optimizer states. And so, of course, I'm going to need an all gather in order to combine them before the start of the following forward. So another way to see it is in the computation communication graph. So I have the forward as before, and then we have the backward. So as I said here, when I'm doing the backward, I need to sum them up. This is true for all like the DP strategies. Every DP rank is going to see a different micro batch. So you can imagine that we're going to have different activations And so when we calculate the gradients, they're going to be different. So we definitely need to reduce in the backward when we use dp. So this part is the same, but it's even faster because, as I said, it's only reduced scatter. It's not all reduced. So we already are faster here compared to dp. But then we also need to add an all gather after the optimizer step. I said that we need to all gather the parameters, which is this. And this is very bad because it's exposed. So how can we solve this? Or not yet, but so how is this different from 0.2? So in 0.2, we said that the gradients are actually sharded. So basically here, since we don't need all of the gradients, why not just keep the gradients we care about? I don't need to store the rest. So this is 0.2. It's not very different. I'm just gonna store the gradients I need, and it actually has the same schema as earlier. And so there is no reason to do 0.1 over 0.2. And I also see that some people still confuse 0.1 with 0.2 actually. So for people who confuse them, always refer to this graph. So 0.1 keeps all of the gradients, and it's 0.2 that shards the gradients. I mean, of course, according to the author's nomination. And this is the most interesting part, which is 0.3, which is, I think, the form of parallelism that's most used today versus TP. I'm not sure which one is most used, but I think there is a competition between both. So what is 0.3? So as we said earlier, maybe let's start with this. So 0.3 is going to shard everything, right? And we can see here that parameters are sharded, and we need the full parameters to do the forward and the backward. So how are we going to solve this? Here comes 0.3. So 0.3, while I'm doing the forward, and as I said earlier when I talked about the CPU offload, whenever I'm going to need to compute something, whenever I'm going to need to do a forward pass in a layer or anything, I'm going to ask for these weights from the other GPUs. So for example, here I'm at layer N. Before, I only had the shard weights because, as I said, each GPU only stores a shard of the weights. And when I reach this part, I need to do my computation. Like I need to do the forward. So I'm gonna all gather all of them. I'm gonna do the forward here, and then I'm gonna flush them. And this happens at each layer, or it can be generalized. Like this is what FSDP call it, FSDP unit. For simplicity, I say that it's done in like at the layer level, but you can define FSDP unit as you want. Like you can do it each like transformer block. So it can be like either attention or MLP, or it can be 2 layers or whatever. The idea stays the same, is that you're going to need to all gather, do the forward, and then flush parameters. And I want to take another minute to emphasize the difference between TP, so for people who are already familiar with TP and still have some confusion with it. So both data parallelism and tensor parallelism, they both shard the model in this way. Like here, every tensor is, every weight is sharded. But for tensor, the weights stay sharded when you do the computation. They're always sharded. Whereas in 0.3, in FSDP, you always need to all gather. And so in a sense, in your code base, you don't actually need to take into account the parameter sharding. Why? Because when we need to do the computation, you're just gonna all gather everything. So from the code point of view, it's like if you always had the full model when you do the forward, which makes FSDP and 0.3, it makes them very appealing because they don't require any code changes. Whereas as we're going to see in tensor parallelism later, they must ensure correctness. They must adapt the code base to be compatible with the sharding of the weights, as we're going to see later. I hope that point was made clear. The backward is the same gradients come. Every time you need to calculate the gradient, you're just gonna all gather the weights. You do the backward pass for your gradients, and then you reduce scatter them to synchronize the gradients. And how does that translate in our graph? So we start by communication this time, because depending on how you implement it. So in this case, I assume everything is flushed, but we can remove this if we want. So we're gonna start with a forward pass. And while I'm doing the forward pass, I can already start all gathering the next layer. And this is the beauty of 03 and what makes it very powerful, because as you can see, it's very well overlapped. So yeah, here I'm gonna do the forward while FSDP call it prefetching, in case you're familiar with that term. I'm gonna prefetch the next layer. And it's the same for the second weight, etc. And since here I'm assuming it's only 3 layers, so it's 0, and then I'm gonna flush 1, and then I'm gonna flush 2, and then I'm gonna calculate the loss, and then I'm gonna start the backward pass. So while I'm doing the backward pass and I'm gonna flush, I'm already gonna start all gathering my weights for the 1, and then I'm gonna do the backward pass, and then I'm gonna all gather my weights, and then I'm gonna do the backward pass, and then I'm done.
So one framing I found really helpful here is like Andrew Gu, who's the author of FSDP2, told me that like FSDP is basically like CPU offloading, but you're offloading to other GPUs. And so like fundamentally then it's like, well, when do I need to prefetch and predict basically where I'm in my workflow? And it kind of all clicked in my head when he said this.
Exactly. Yeah, for people who are familiar with CPU offloading, it's exactly the same thing, and it poses the same questions and the same risks. So the question is, when do you prefetch? What's the size of your FSDP unit? Basically, how much do you prefetch at a certain point of time? Because if you prefetch the whole model, that's impossible because you need to start somewhere. But yeah, let's say you're gonna prefetch the half of your model, then you're not saving up memory. Actually, you're already having half of the memory consumed. And if you have like a very small granularity, then you're gonna need to do a lot of prefetching. So the question is, can you really overlap it? So yeah, there is a trade-off there. The other issue that 03 faces is the number of collectives. You can see here, compared to the previous methods, like the entire forward and backward are full of communication collectives. Each of them comes with a base latency, and of course they depend on the max throughput. And each of them is all gathered and then reduced scatter. So it's like you're doing a lot of all reduces compared to the first DP we had. So they are not very network friendly, we can say, because they require a lot of communication primitives. So here you can find
Guys, I think this is probably a great time. I'll have to drop. This is amazing work. Thanks to you and the whole Hugging Face team that has done this. I enjoyed reading it a few days ago. I actually submitted an issue on Hugging Face, so hopefully you corrected it, a couple of typos, but generally very, very, very cool work. Mark, thanks for invite again.
Thanks for coming, Alexa. Appreciate it.
I'd love to be here 8 hours, but I'll have to drop. Bye, guys. Cheers.
And yeah, I think we took more time in DP because it had a lot of things, but hopefully some parts are much shorter, like context parallelism and expert, I think, are much shorter. So hopefully I'm gonna stay within the 3 hours limit. And so what does this mean in terms of memory usage? We're gonna notice here something very interesting. So let's say I have 8 GPUs. right? And all of them, they use data parallelism. So when I use data parallelism without any zero technique, I'm going to notice that, well, I have, first of all, the full model. It's not sharded. Optimize, like everything is full. Like the model parameters are full, gradients full, and optimizer states are full, and activations, of course. When I do 0, 1, optimizer states are divided by 8. When I do 0, 2, I'm also going to shard the gradients. So the gradients are going to be divided by 8. And activation 0, 3 is going to shard everything, which means the parameters as well. But the question is, why aren't activations being sharded? And I hope that people have been following us. So as I said here, from a code base standpoint, at every layer, I'm gonna all gather the entire weight. So my activations are actually always full. It's like if I had all the model, like the entire model every time. And so I don't actually save up any memory in the activations, which is why in order to, because activations can quickly take up a lot of memory, which is why memory recomputation becomes very important in the case of 03. Basically, you only store activations in like between your layers, for example. So I'm only going to store activation here and here, not everywhere. I think in this graph, I wasn't, in here, I'm not using any recomputation at all, which is why it doesn't really go down. But if we use activation recomputation, then activations will also go down. And I think it's time to take our first break before going to TP.
Okay, so like I guess we can go over like a couple of questions now. So Apaz had a question around the bucket, like basically the DDP bucketing stuff. So he's basically saying the bottleneck should be bandwidth, not overhead. What if you hit it on another thread instead of bucketing? Or is it the all reduced kernel launch time that you're bucketing for?
Sorry, I didn't. Can't we show the question in the?
We could actually, yes. Let me do that. Here, show the question on the screen.
Yeah, much easier. Thank you. So, I'm not sure what the user means by bottleneck should be bandwidth. Like it can be both. It depends on your network and it depends on your thing. What if you hit it in another thread instead of packetting? And what do we mean by thread? So as I said, in GPU computation,
I think they mean a stream is how I would interpret this question. Yeah.
Okay, so let's say we have multiple streams. The bottleneck will be the network channels, and the channels are limited. So even if you have multiple streams, they're gonna compete on the same, basically the links between your multiple machines, right? So it's not actually a question of the number of streams. It's even if you have two streams, they're gonna use your communication links at a certain time with a certain base latency and a high bandwidth. I hope that answers the question.
Yeah, I think they got it. They said it sounds like network overhead is the TLDR. Okay, so the second question was, I don't think I fully understand the question, but it's like by Amin. And they're asking, is this why DeepSeek used 20% for communication?
Yeah, I don't remember the reference, but yeah, maybe if they can provide the 20%, where does it come from?
Yeah, maybe, I mean, if there's more detail, we can sort of like answer your question in more detail in the next chapter. So the last question is from Rohit, which is, they like thinking of FSTP as CPU offload, but for GPUs, and they're wondering if it's possible to have data parallelism with CPU offload and an all reduced for the gradients as a faster alternative to FSTP.
So DP with CPU offload and an all reduced for the gradients as a faster alternative. So faster, I would say no, because once you put CPU into the equation, you're gonna be hit by the memory network bandwidth, which is the slowest out of the three. So as I said, so yeah, we didn't include a graph with the different like bandwidths. But as I said, so in a single node, you have NVLink, which is the fastest. Between multiple nodes, you're going to use EFA or InfiniBand, which are okay-ish in terms of communication. But once you do GPU, CPU communication or GPU, CPU disk, that's the slowest in terms of bandwidth. And so you absolutely do not want to include that while training. But you said that we can use it if we can overlap it correctly, then yes, it would be a viable option. But I don't really. So where would you include that? I mean, so 03 already does that. In this case, that would be just 03.
All right, yeah, and then so Amin also clarified his previous question, which is why did they use 20 SMs or 20% of the SM? So basically, it's like the trade-offs between how you balance communication versus computation among your SMs is the heart of the question.
Yeah, that comes a bit later. Maybe we can talk about that. So I'm just gonna point you to where to read about that, but so yeah, it's in this part that we talk about the not so perfect side of communication and computation overlap, and I think we put a link here. And this is a great discussion by by Wong and all of the authors here, and they talk about SM occupancy and SM's contention in communication, and I highly recommend you to read about it to understand like what does that entail. Basically, there is no clear answer to this, but yeah, it's currently an active area of research.
All right, excellent. I think if that was a good long enough break, I think we can keep going.
Sure. So I think data parallelism and tensor parallelism are the most complicated to understand. Hopefully that viewers are still following up. But once I'm done with tensor parallelism part, it should be a slide for the rest. So let's try to tackle this. So the smallest example we can start with is you have a weight. A weight can be represented this matrix, and you have inputs, right? Your inputs is, for example, the hidden states from your previous layer. So you're going to multiply them and you get an output. Now, we, thanks to the properties of matrix multiplication, we can do this matrix multiplication in parallel. How do we do that? We're going to take this weight and we're going to shard it over two GPUs. So we're going to have W0 and W1. We're going to have the same input in both our GPUs. We're going to do the multiplication on each shard, which is going to give us Y0 and Y1. And then I'm going to need to all gather them, as we explained previously. All gather them means I'm just going to concatenate from the different GPUs, and I'm going to get the same result as earlier. Cool. So what do we call this? We call it column linear, because I took this weight and I sharded it like vertically. There is also another way to do this. It's called row linear. Row linear means so again, going back to this example, I'm gonna take my weight, I'm gonna shard it, but this time horizontally. I'm gonna get W0 and W1, but I'm also gonna shard my input. So I had X here, I'm gonna also shard it like this vertically. And I'm gonna do the multiplication, I'm gonna get Y0 and Y1, and then I'm gonna all reduce to again get the same output as earlier. So we can see here that there is two ways of doing this matrix multiplication, but in parallel. And this is the forgot the word, the reason, the motivation behind tensor parallelism. So basically, since our matrix multiplication take up the most compute in our like LLM's training, why don't we do this in a distributed manner? So each GPU is going to take a shard of our linears, and linears take up the most space, the most size in our transformer, and we can do that in parallel. But as we can see here, and as I explained earlier, I'm gonna shard the weights, and I'm gonna keep them sharded. I'm gonna use some properties to ensure correctness, which is not always the best when you wanna try different architectures, like let's say Mamba, some new forms of attention MLA and stuff. But yeah, anyway, let's go back to our example. So how does that look when we combine both column linear and row linear? So let's say I want to do two matrix multiplications. So I'm gonna have W1 and W2. Both of them are sharded. I'm gonna have the same input. I'm gonna start with the same input. So as I said, column linear works with the same input. So I'm gonna keep the same input. And the column linear is the one responsible for sharding the input. And this is very interesting. I like to think of it this way. The column linear shards the input and takes the same input in the, like both GPUs, they have the same inputs. Whereas the row linear, it requires sharded inputs. So it takes Y1 and Y11, and it gives back like some intermediate results that I'm gonna need to all reduce. So the way I understand it, column linear will just do like, you're just gonna multiply and you're gonna have sharded outputs. And the row linear is both this matrix multiplication and this all reduce in order to get the output. And this is it. This is the technique behind tensor parallelism. And why is this interesting in the case of transformers? Because we always have two big linears. For example, in attention, we have the QKV projection, and then we have the out projection. So we usually do the QKV projection as a column linear, and the out, yeah, there's an example here. I don't know why I'm explaining it. So let's take the example of self-attention. So in self-attention, we have two linears, right? We have the QKV projection, and then we have the out projection, which is B1 and B2. Here we didn't show the weights, but we can say it's Q1, K1, and V1. So I'm gonna take this linear, which is the QKV projection, and this linear, which is out projection, and I'm gonna shard them on two GPUs. And of course, once I shard them, it's already good for me. Why? Because I'm gonna save up memory. And once I'm gonna have TP8, that means that my weights are gonna be divided by 8. But now what did I say? I said that column linears, they require the same inputs. So that already complicates my assumptions. So for example, when I was talking about 0.3, I didn't talk about activation at all because they don't touch activation. They're always the same. But once I start working with tensor parallelisms, and I get a lot of this question like, hey, I'm trying to add tensor parallelism to my code, but it doesn't work. Or I'm trying to add d-tensor, but it doesn't work out of the box. Why? Well, maybe because the model doesn't support it, or like, yeah, you need to respect these assumptions in order for TP to work. So yeah, as I said, we need a column linear here. The column linear here requires the same input, otherwise it doesn't work. And then once you do the out projection, which is B1 and B2, So the out projections, the row linears, sorry, I said that they require sharded inputs, which is y1 and y2. They're going to give intermediate results, z1 and z2, that we need to all reduce in order to get the correct output. So if I want to, for example, verify the correctness of this, let's say I'm debugging Nanotron or a distributed library, how can I debug this? So I'm going to try with TP2 and with, so for example, I'm going to try with 2 GPUs and with a single GPU. So I must notice that the input here is the same on GPU1 and GPU2. I must notice that the intermediate activations here, or the hidden states here, are sharded. Like all of this is sharded along the hidden dimension. And so, for example, if I concatenate something from here with something from here, it should be the same. And at the end, when I do this row linear, Z1 and Z2 are going to be different. But once I all reduce, this result should be the same as the case of 1 GPU. I don't know if I made it clear, but hopefully if the implementation is correct, like if your column linears and your row linears are correct, this like operation should be equivalent whether you have like multiple GPUs or whether you have single GPU. So this is tensor parallelism. Another comment is this dropout. So this dropout complicates things. For now, luckily, we don't use it anymore. But in the case of in case like someone uses it still, you need to make sure that the seed is fixed across the GPUs, and that's not evident at all. We have some very ugly decorators in Nanotron to do that. Yeah, it's better to just remove them to make life easier when you use TP, or when you have dropouts, it should be easier to like not do TP but use another form of parallelism. But yeah, this is a small comment about dropout. The latest LLMs don't put dropouts inside of attention or MLP, so it should be all good. How does that look like in terms of computation communication overlap? So I'm going to take the example. Yeah, so this is for self-attention, but for MLP, it's kind of the same thing. So I'm going to take the first linear, then activation, then the second linear. And then I need to all reduce, because I said that the first linear is a column linear. Column linear doesn't require communication. But the row linear, it requires an all reduce, which is the exact same. Here, column linear doesn't require any communication, but the row linear requires an all reduce. And the other thing to pay attention to is that, so TP is applied to both self-attention and MLP. But what about the regions between the two? I'm going to fast forward to here. So in here, so there is tensor parallelism and tensor plus sequence parallel. So what's the difference between the two? We have TP that is applied here to self-attention and the output projection. And here we have TP that is applied to the MLP, which is in this case, the two linears. And we can notice that TP does not affect this area, which is basically the area between self-attention and MLP. It can be anything. It can have layer norm dropout. It cannot have anything. It doesn't matter. But basically, TP only affects the self-attention and the MLP. And why is it the case? Because as I explained earlier, so TP consists of column linear. In this case here, it's going to be QKV projection and out projection, column linear and row linear. And in the case of MLP, the first linear is a column linear and the output is a row linear. So this is the idea behind tensor parallel. So thanks to Tensor Parallel, what does it mean for throughput? So in this case, and basically this is a naive way to do TP. I know that now there are better ways to overlap TP with like communication and computation. But I think if you want a correct and fast forward implementation for TP, you're gonna end up with an exposed or reduced here. So what does it mean? Well, once you have TP in a single node, which means in our case, we use H100 nodes. So we have like 8 GPUs in a single node. So the 8 GPUs are connected with NVLink, so they have high throughput. So we noticed that when I'm scaling from 2, 4, 8 GPUs, I'm not losing efficiency a lot. But once I move from 8 to 16, I'm gonna notice a very big drop in efficiency, so a 42%. And when I move from 16 to 32, it's another 65% drop in efficiency. Why? It's because of this exposed collective. And again, as I mentioned, this is specific to the implementation we have in Nanotron. So it's not the perfect one. And as I showed earlier, just in this blog, people are talking about a better way to do async TP. You can check out the recent DeepSeek repos, where they also have open sourced some deep gems that are also like a form of TP, and they do a better overlapping between computation and communication. Basically, the idea would be to overlap this all reduced with something else. But before taking questions, let's see how it affects memory. So as I said, so this is the example of a 70 billion model. With no parallelism, this is the memory usage consumption. Once I scale the TP, I notice that everything is going to be sharded. So the model parameters is divided by 8, activations, the gradients, are divided by 8, and optimizer states are divided by 8. But I noticed that the activations are slowly reduced, not very much reduced. Why? Because I still need to save some activations in full dimension. For example, here, between the, like, once I enter dropout, and like, these activations are full, because I said that activations here are sharded. What? Because we explained earlier. But after I all reduce, here I'm gonna have the full activations, so they have the full hidden dimension, which is why I don't notice big gains in activations. And so the question is, can we shard activations here as well? And can we parallelize the workload in the dropout region as well? And yes, we can. And here comes sequence parallelism that tries to parallelize the workload in the left out regions. So basically the regions between self-attention and MLP, and the region between MLP and self-attention, etc. Now, why wasn't it evident to do it in the first place? Like, why did people come up with TP and then tensor and sequence parallel? And why is it called sequence parallel in the first place? Well, because in TP, we were trying to shard across the hidden dimension. Why the hidden dimension? Because as we've seen earlier, we were sharding the matrices. And when I'm gonna shard the matrices in here, I'm gonna notice that it's the hidden dimension that is being divided by the number of GPUs. But I always keep the sequence intact. But there are some operations like layer norm that require the full hidden dimension in order to be computed. So here, layer norm needs full hidden dimension. So I can't actually shard hidden dimension, but I can shard the sequence, because in the layer norm expression, it doesn't depend on sequence, which was the motivation between sequence parallel. Instead of sharding So in TP, we shard on hidden dimension, because when I shard the matrices, they shard along hidden dimension. And for this region, I'm gonna all reduce or all gather, it's the same thing. I'm gonna restore my hidden dimension, and I'm gonna shard across sequence dimension, because these operations are independent along the sequence dimension. And for more details, you can read about this part, where we also try to explain how the dimensions change. So for example, in the TP part, you notice that it's hidden dimension that's being sharded. And in the SP part, which is the sequence parallel, it's the sequence that's being sharded. And of course, it ensures correctness. So how does, or what does this entail in terms of communication? So in here, we've seen earlier that column linear doesn't require any collectives. And yeah, I just remember that. So far, I've always been talking about the forward pass, like even here as well. When I was talking about this, it was the forward pass, but we're gonna see later that the backward pass is just the conjugate. So yeah, just follow up with me and you can see that later. So talking about the forward pass again, the column linear doesn't require any collectives, any communication. So F here is a no operation. And F star here is an all reduce. Why? Because the row linear needs to all reduce for correctness. In here, G is all gather, and G star is reduce scatter. Yeah, you can try to make sense of them later, but you're gonna find that this is the only way for it to work. So, and here we, give me a second.
This is like again on the dot with an hour.
Yeah, second. Sorry, and yeah. So as I was saying, yeah, G here is an all gather, and I think yeah we talk about here, and G star is an reduce scatter. I know that this is confusing. It wasn't very easy to understand at first, but hopefully, if you take time to read through this, everything is gonna make sense. Just remember that in TP, the column linear will shard the activations. The row linear is going to restore the hidden dimension. And then the G star is going to reduce scatter along the sequence dimension, so that we're gonna have the sequence divided by 2. Yeah, feel free to replay this part to grasp it easier. And for here we made like a summary table, case of TP only and TP with SP, and how does the dimensions change. So in the TP region, or once I enter TP, in the case of TP only, so the column linear is going to shard H. Why? Because the weight out is sharded, and sequence is always full. In TP, sequence doesn't change. In the TP region, hidden dimension is sharded. Once I exit TP, I'm going to restore H. And in the SP region, which is the layer norm region, hidden, so both are full. This is why I didn't save up any memory before. But thanks to sequence parallelism, once I enter TP, so H is sharded the same way, and S is full. This is why I need an all gather before it. So you see here, it's going to all gather S, the sequence, I mean. H in the TP region, H sharded is full, similar to TP only. When I exit TP, the hidden H is full because white out is full, but S becomes reduced scatter. Why? Because I do a reduced scatter. Reduced scatter comes from So the reduce comes from the row linear to ensure correctness, and the scatter is to scatter the sequence. And this is, takes time. It took time for me to understand. And just to understand like the code base of a lot of code bases, Megatron, Deep Speed and stuff, it's not straightforward, and you find a lot of stuff about it. But this is basically why do we have a reduced scatter. The reduce is to ensure correctness from the row linear, and the scatter is to shard along the sequence dimension. And then in the SP region, you're going to have sharded S and full H, and then you continue the cycle, and then you're going to enter TP again, etc. So this explains all of the model except for the embedding layer. So at the start, of course. So at the start, you're going to have an embedding layer, and it's a row linear sharded on vocab. So you're just gonna, if it's vanilla TP, you're just gonna do all reduce because it's a row linear, and S is the same. But in the case of SP, we're gonna do a reduce scatter for correctness. And thanks to this, so basically the only difference is that we're not gonna store activations in the SP region, which means I'm gonna gain more, or I'm gonna save up more memory in the activations. And so as I said earlier, so when I use TP with SP, I'm gonna need an all gather in order to gather my sequence dimension, and then FC1 is a column linear, so this is sharded along H, and then FC2 is a row linear. The row linear needs a reduce in order to ensure correctness, and then I'm gonna scatter along the sequence dimension to enter the SP region. And we can already see that since it's very hard to overlap. Why? Because in order to start the reduce, I need to first calculate the multiply. So in order to, for example, overlap these two, it's gonna need to be a very complicated method where you're gonna take your matrix, like separated in multiple blocks, and then try to overlap each part, which is why, as I said, it's not super easy to implement, which is why in here we showcase the naive way to do TP, currently implemented in Nanotron and also a lot of other libraries. But ideally, we can overlap these operations better. And the difference between TP, just to refresh our memory. So in TP, I only had one all reduce, which comes after the row linear. But in this case, I have both an all gather and a reduce scatter. But as we've seen earlier, an all reduce is almost equivalent to all gather plus reduce scatter. So in terms of bandwidth, in terms of communication, they are equivalent. But since here it's two memories, there is a base latency here. That's bad. But overall, they should be equivalent. And as I said earlier, so TP with SP, it has the same behavior as TP in scaling. So inside the same node, I don't notice a lot of performance loss. Okay, this is actually bad because so here I have two operations that are exposed, and my assumption that all the reduce is the same as all gather and reduce scatter is not always true. It also depends on the runs I had for this. Maybe this run had a very bad throughput for reduce scatter, etc. So it's not always like these numbers are to take with a little like grain of salt. But the idea is that once you go through when you move from internode to when you move from intranode to internode, when you move from a single node to multiple nodes, you're gonna notice a big drop in in efficiency, in throughput scaling, mainly because you're going to start using the network instead of just the intra-node and the NVLink, basically. And what does that mean? Well, since I'm going to save up memory, that means I can fit more batches in a single TP value. Cool, that's TP. I think it's time for our second break. And so, yeah, so far, if you have been following with DP and TP, these are the two most complicated forms of parallelism. And as we're going to see later, now it's most a slide from here on.
Okay, yeah. I guess let's see in terms of I'm still going through the questions. I guess a lot of your questions were answered. There's one maybe by Amin. I'm going to post it on chat.
Okay, can we change the layer norm OP to have better overlap? Ideally, we could have norm. Yes. So yeah, so you talked about changing the layer norm to have better overlap. We can also change the matrix, not change the matrix multiplication, but like just make it more granular so that you get to overlap more. If you take a look at Deep Gems by DeepSeek that were released this week, they have some very nice diagrams that explain it. So yeah, like if it depends on how much control you have and how motivated like to have a granular implementation. But yeah, you can definitely overlap better your operations.
I guess like on this topic of DeepSeek, Calvin's asking.
Yes. Well, I'm not. Yeah. So the question is why DeepSeek avoided TP. Yes. So for DeepSeek architecture for people don't know it. So they basically introduced two main changes, which, so yeah, MOE, we're gonna see later, but there's also MLA. And MLA is not very straightforward to add TP to, because as I said, TP mainly needs a column linear and a row linear in order to work. But in here, they have some adapters, they have some keys that are shared. Yeah, it's not very TP friendly. And as I said, there's not, so 0.3 can work just as good. So maybe, but I think DeepSeek went with 0.1 and PP, if I'm not mistaken.
All right. No, I think these are all the questions.
Cool. So yeah, from here on, let's try to tackle the three final parallelisms in the final hour. So CP, context parallelism, comes from this. So yeah, let's first look at the issue that we didn't tackle yet. Once we want to scale our sequence length, and we've heard lately that there are a lot of models with like very big context lengths, like even 1 million. Activations start becoming like a big issue, because as we've seen earlier, DP doesn't really help solving activation memory unless you do recompute. But when you do activation recomputation, that means you're a little slower because you need to recompute your activations. On the other hand, when you do TP, you're limited by within a node. So as I said, the TP is mostly used within a node. So TP is usually smaller than 8. So we need another form of parallelism in order to scale our sequence length efficiently. And that comes, this is inspired by flash attention. Not inspired by, I don't remember who came first, but basically they use the same technique, and they both count on the concept of online softmax. Basically, in order to do the QK transposed, you don't need the full Q and the full K. You can do it like you can overlap it. You can do it sequentially. What does that mean in a distributed manner? So let's say each GPU is going to have a shard of your queries, Ks and Vs. So everything is sharded, right? Actually, because why is everything sharded? Because the sequence is sharded. So let's say we shard the sequence, right? Let's say I have a very long sequence and I'm gonna shard it on 4 GPUs. And so of course, if the sequence is sharded, then Q, K, V, everything is sharded. Everything is different. Now, in order to compute Q, K transposed, obviously I'm gonna have QK, like for example, GPU1 already has Q1, K1. So I can already calculate Q1, K1 transposed. So we calculate that, then we pass it along to the second GPU. And I get K2 from the previous GPU. Then I can calculate Q1, K2 transposed, etc. I think the idea is clear. And then, yeah, I can compute the attention score like this sequentially in order to like have the same attention. I don't know if I did a good job explaining it, but it explained like this graph, I think explains broadly how it works. There is also two different implementations for this. But first, okay, so we quickly talked about the different attention masks. So the naive attention mask would be for each GPU to try to attend to, well, the tokens as they come up in the sequence. But we can see here that GPU1 only needs to attend to the 4, so the Q1, whereas GPU4 needs everything. So a better way to balance compute would be like this. She's called zigzag ring attention or stripe attention. Yeah, this is just to balance compute. But then there is two ways to do ring attention that appeared in both Megatron and DeepSpeed. One would be, so for each GPU, let's say the GPU index is I. For each GPU, I'm gonna calculate Qi, Ki, Vi, so for this GPU. At the same time, I'm gonna gather all of the other keys and values. So it's not the best in terms of memory, but it's faster. So while I'm doing this, I can flush this and I can compute the rest. So Qi and the next K and next V, etc. The other way to do this would be an all-to-all communication. What does it mean all-to-all? It's exactly like the schema we had earlier. So while I'm doing Qi, Ki, Vi, I'm gonna fetch the next key and value I'm gonna use, and then I'm gonna calculate attention using these two, I'm gonna fetch the next one, etc. And this needs a lot of P2P, means point to point, means GPU to GPU. Basically, fetch means send and receive. Each time I'm gonna send my K and V, and I'm gonna receive my K and V. So yeah, it requires a lot of send and receives, which is not very optimized. Usually we prefer all gather because they are more optimized in terms of a collective. Because yeah, that's probably for another talk. All gather collectives are more optimized than all to all at the current, unless you write your own nickel or your own collectives. So here we put basically a summary of what I've just talked about, and this is it. This is context parallelism. So to summarize, I'm gonna have different sequences go through the model, And the idea is that the attention, and only the attention, is going to be affected. The attention is going to be done in a distributed manner. Why do I only care about the attention? Because it's the only one which has activations that scale quadratically with the sequence length. I think we have a table for the activation memory later on. But yeah, is there any question? Otherwise, in the final part, we're gonna understand this.
Yeah, I don't see questions right now, so maybe we can keep going.
Cool. And then comes pipeline parallelism. And here it comes from the issue that network very quickly becomes very bad. So here we're plotting all reduce, all gather, reduce, scatter as we scale the number of nodes. So in a single node, I have an all reduce with the best throughput. And we can already see that all gather and reduce scatter are almost half of it, which validates our assumption for earlier. And then as I move on to two GPUs, all reduce is still better than all gather and reduce scatter, is still almost the double. But once I go to 4 nodes and more, like all reduce becomes very bad, and everything basically drops down very fast. So basically, the idea here is that bandwidth degrades very quickly, and whereas like TP and DP require a lot of collectives. So how can we reduce the number of collectives? Here comes PP. PP is the parallelism with the least number of collectives that still shards the memory. So we said that DP, it's also like it's the one with the least number of collectives because it only syncs the gradients, but it doesn't shard the model. But PP, it does shard the model, and so once we shard the model, everything becomes sharded. But it keeps the same activations, similar to 0.3, which is why we usually compare PP with 0.3, because they kind of have the same benefits and kind of the same drawbacks. And to understand PP, we're going to start with this very simple case. So we've seen how to shard each operation. For example, in TP, we sharded every linear. And in 0.3 with DP, we would shard the model, we would all gather all of it, and then we would flush it. But in PP, we're gonna shard along the layers. So the GPU1 is going to have the first 4 layers, GPU2 the next 4 layers, etc. And so when I'm gonna do the forward, so the input starts from the first GPU, I'm gonna do the forward, then this GPU is going to send the activations to the second GPU, I'm gonna do the forward, etc. And the backward is the opposite. So once I reach this step, I'm gonna send the gradients to this one, etc. And then I'm gonna do the optimizer step. We can see that the biggest issue with PP, this is called the all forward, all backward. I don't know if talk, yeah, all forward, all backward. The all forward, all backward sequence. I don't remember the name. The PP schedule. Yeah, sorry. This is the all forward, all backward schedule. And as we're going to see later, we can have multiple PP schedules, each with their own pros and cons. So in this case, this PP schedule has a lot of idle time. As you can see, it's the most naive one. So how can we make it better? We can try to compute the bubble time using this formula. Anyway, so a better approach would be to send a lot of micro batches and do, for example, GP1 is going to do a forward and then send the activation. And while waiting for the backward, the first GPU can already do the forward for the other micro batches. So this is why, this is also all forward, all backward, but it has multiple micro batches. So we don't really need to wait for the single micro batch to go through all the GPUs and then go back. So this is the difference between this and this. A more interesting approach would be one forward, one backward. And the general idea is that, so I'm going to have 4 micro batches. So the first GPU is going to forward, send activation, and do forward, send activation, forward, send activation, forward, send activation. And the last GPU, once it does this forward, it's already going to do a backward, and then it's going to send the gradients. Same. So that in the middle, we're going to have one forward, one backward, one forward, one backward. So we're going to try to interleave the forwards with the backwards, as opposed to this one, where we used to do all forwards and then all backwards. So what's the difference? The difference is that once I reach here, I'm going to do forward, and then I'm going to do backward, and then I can flush these activations. Whereas in here, once I do this forward, I need to save these activations because I didn't do the backward yet. So I need to store these activations, and 2 and 3. So I need to store all the activations for all the batches before starts doing the backward, which is why in general, when we do PP, we try to do the backward as soon as possible, because once you do the backward, you can free the memory. Or in order to free the memory, as we've seen earlier, we can do activation recomputation. So activation recomputation works all the time. So you don't need to store anything. You can have this one. You're not going to store anything, and you're just going to recompute them at a certain point of time. I think that's the difference. Yeah, and all the time, yeah, you can find some implementation here. So yeah, PP is it's much easier. So basically, we're just gonna short the layers. What does that entail in terms of throughput? And again, that also depends on Nanotron implementation with our network. So here there's something interesting. The biggest problem with PP is this idle time, what we call the pipeline bubble. Bubble because it's just bubbles that appears when you do the forward and backward. So ideally, you want to minimize this idle time as much as possible. There is some formulas to estimate in it. No, actually, I didn't. Oh. Yeah, so let's, I think, look at this one as well. So interleaved 1F1B. Yeah, it's more complicated, but the idea is that, so you're going to define, I think they're called stages. Yeah, let's call them stages. So in dark blue, it's the first stage. In light blue, it's the second stage. And each stage has 4 micro batches. So you're going to do the forward for this stage, and then the forward for this second stage. But then you're going to do the backward, as I said, as soon as possible, for the forward for the first stages. So this is the backward for the first stages. And then at the same time, you can see that there is already the forward, the second forward for the first stage that kicks in. But yeah, I think you understand that if you just take a look at the difference between this and the previous one, you can understand what's happening. Basically, you have 2 stages, forward, backward, forward, backward. And since we add more granularity into these micro batches, you can overlap them better. I think it's better to put this in schema than in words. And now we also have formulas to estimate the idle time. So this idle time, which is called the bubble time. And in the case of, okay, let's start probably from the 1F1B. Okay, so this one. This is so AFAB. In the case of all forward, all backwards, so the bubble was the number P. P is the number of GPUs minus 1. In the case of AFAB with multiple micro batches, it's P minus 1 over M. So it depends on both micro batches M and the number of GPUs. And it's actually, even when you do one F1B, it's going to be the same formula for the bubble. So the only difference between one F1B and this one, AFAB, it's in the memory usage, not in the bubble. It, like one F1B doesn't actually reduce the bubble time. And then in interleaved does reduce the bubble time, and we're going to notice it's P minus 1 over V times M, where V is the number of stages. In this case, we have 2 stages, dark blue and light blue. Cool. And there are more fancy, like with DeepSeek, there's even a fancier schedule that you can take a look at. Of course, again, the idea is to reduce this idle time as much as possible. So this is why 0.3 is still preferred over PP in a lot of cases, because 0.3 doesn't have this idle bubble time. Like it's very well overlapped. But again, PP schedules are also advancing. Like we've seen with DeepSeek, they have very, I think we can take a look at it. It's called Leopard.
Which maybe then I'll also batch a DeepSeek question again in chat, which is Amin is asking, why is writing your own common PTX better than nickel for non-all gather ops?
Because you have more control over what the operations do. Because I don't know if you, I think you, since you asked this question, you're probably already familiar with it. But using nickel API, especially through Torch distributed APIs, you're limited by what the API lets you do. For example, in the case on all gather, for example, you need to have, for example, the same tensor sizes in order to, for example, let's say you have 4 GPUs. Each GPU is going to have the same size for the tensor. You can't concatenate a tensor of 1 size with a tensor of 5 sizes. For example, this is a small limitation. I don't know if it was solved yet or no. But yeah, stuff like this will enable you to, if you write your own PTX, you can control everything, basically, the way you do communication. And as another user asked before, you can also start overlapping better your operations. For example, while you're doing the matrix multiplication, you can already start all gathering or reduced scattering specific like blocks of the matrices, and you can like control the warps, you can control the SMs, you can control everything to ensure the best throughput possible. But again, that requires a lot of infra work, and it's very hard to maintain. So it's not evident to have like an open source library that would implement this and keep it maintained. But we hope through this work that more people start looking into this, collaborate, and making better, not better, but making more contributions in the parallelism space.
Sounds good. And I guess a question I had on my end, which is like, as you were going over all the pipeline schedule, it's interesting because like data parallel is effectively like one algorithm, but like pipeline parallelism is sort of a family of algorithms. And so like in this vein, have you found it easy to sort of like experiment with different schedules without having to change the rest of your pipeline scheduling code base?
Yes. So yeah, I remember. I think in one of your previous talks, you cited Andrei Karpate's tweet about pipeline parallelism. I think
Generally unwise is what I've heard people describe it.
yeah. Nanotron. Well, at least the version that we have actually in Nanotron, we try to have a general and easy to put, like easy to implement pipeline engine. Basically, our pipeline engine is kind of transparent to the schedule. So you're gonna have a part where you define your pipeline scheduling, and then when you do the modeling of your model, you can, for example, add wrappers, for example, to the MLP or to each layer where you're gonna define your PP stages, etc. And so we try to do it in a simple way so that anyone can add any schedule they want, etc. But as I mentioned earlier, the problem with some schedules is that they also touch the data inputs. So for example, here, once you're going to define multiple stages, that means you'll need to update your data loader to take into account that change. And of course, in the Nanotron's pipeline engine, the backward is immediate. We rely on a trick to do to reuse the autograd, PyTorch's autograd. But is it the most optimized way or not? Yeah, that's also a question. So there is the ease of use, the ease of research to experiment with new things versus performance. And usually, if you want to push for performance, the code base gets uglier.
Understood. Okay.
Yeah. And another thing, plug in a little bit Nanotron here. The other cool thing that I like about Nanotron is that we tried to gather all forms of parallelism in a single library. So yeah, for example, unlike some other libraries, okay, so it has its own pros and cons. So for example, if we use Torch Titan, it has fewer lines of codes, which is great, and anyone can, for example, just see it as an example and take the TP part and implement it in their own code base, which is very clean and very good. But in Nanotron, for example, if you want to play in the combination of PP and TP, in the case of Torch Titan, you're gonna need to go through the PP, I think it's called, library, and the dtensor library, and you're gonna try to fix, or you're gonna try to make both work. Whereas in Nanotron, everything is defined from scratch using Torch APIs, and like PP is defined from scratch in Nanotron, and TP is defined from scratch in Nanotron. So that enables an easier way to experiment with things. But of course, at the expense of a bigger code base and not a very straightforward one. And it's also harder to maintain compared to Torch Titan, for example. I hope that I explained the pros and cons of each library. And so to finalize PP, to take some more questions. Okay, we talk about zero, I forgot. So yeah, the final dual pipe schedule is the one I just showed by DeepSeek. And it reduces the bubble a lot. It's also, you can see here that the main benefit is that they also try to overlap the backward for input and the backward for weights with compute. So it's like they added more control over what the backward is doing so that they can better overlap it with compute. So this is what I meant by once you, if you want to have better performance, you're gonna need to implement your own collectives, implement or hack your way through the existing APIs. And the benefit is that you're gonna have great performance. Cool, that sums it up for PP. And there is our last parallelism, which is expert parallelism. Is there any questions about this?
I think we already covered the PP questions, so we can keep going.
Cool. Yeah, the last one is a very short one, expert parallelism. So expert parallelism, as the name entails, only works for experts. So it's only when you have an MOE mixture of expert architecture. You can find here a blog post that explains MOE. So yeah, for expert parallelism, actually, I was surprised to see a lot of people still confusing the different axes of parallelisms. So basically, yeah, there is no single way to define EP, but in this blog, we try to define it in a simple way. So expert parallelism, in our case, means we're gonna parallelize the experts along different GPUs. So each GPU is gonna get a different expert or multiple experts. And then, so what does that mean? So if each GPU gets a different expert, that means that attention is the same. So every GPU is going to do the same computation for attention, which is bad. So ideally, you want to give each GPU a different batch of data, either a different sequence or like a sharded sequence or a sharded micro batch, because sequence, like your input tokens, has both the dimension of a batch and the sequence. If you shard a long sequence, which is summarized in this nice graph, so data and expert parallelism means that your inputs are going to be sharded along the batch dimension, which means that your attention would work fine. Why? Because you have your full sequence, so you don't need to change anything. And since x1 and x2 are different, then you're not duplicating compute, which is good. So every GPU is doing its own compute. But of course, when you're going to reach the router here or the gate, you're going to need to, or you want to be able to communicate your tokens freely among all the experts. So here you can have an all-to-all. So every GPU can route some tokens to the other GPUs, etc. So expert parallelism requires an all-to-all communication here to dispatch the tokens, and then you do the experts calculation, and then all to combine again or get back the previous input tokens and decode, and then you get back to a simple you get back where you started from. So y1 and y2 with the same dimension that you started with. So in this case, expert parallelism took different batches of data, which is why in this paper they call it data plus expert. We can also envision a way to shard the experts along TP dimension. So in this case, it's like they decouple TP and expert axes, which makes it a little more tricky to understand, because so ideally I would just keep every axis different, just like we did with context parallel, so that for people to easily understand it. But the idea is that you can shard your experts the way you want, either on previous like PP or DP or TP, or you can define a new axis just for EP and have different batches. In the 5D, in the summary, we're gonna understand this part better. But the idea is that your experts are going to be sharded and you're gonna need an all-to-all communication. Is there any questions for EP? EP, which is expert parallelism?
No, I think we can keep going. Yeah.
Yeah, I think we're gonna make it in time.
It's like you still win the record, by the way, even if we end right now. So like, I think now this is just like, flexing.
I'm glad. And I think, okay, so this is the most important part of the blog post, I think. Yeah, we took quite some time to polish it. So yeah, we've covered 5D parallelisms, but actually you can have like even multiple parallelisms. Like there is also vocab parallelism that parallelizes the vocab. Loss parallelisms anything, basically anything that you distribute, you can define a new axis for it. So why do we have multiple axes? And I think this is well explained in the llama graph. Did we keep it at the end? Okay, I don't think it didn't make the cut. Do we have it in the conclusion? Maybe here? Yeah, here. So why do we have different axes? Because as you can see here, so you have, for example, GPU 0, 1, 2, 3. So when I say the TP axis, that means that every 2 GPUs in this axis are going to communicate between them. When I see CP axis, that means that these two GPUs are going to communicate. So this is the idea behind the axes. And what's the cool about this thing is that every axis is independent, unless say different. For example, for expert parallelism, some people couple it with the DP, because as we've seen, we can shard the patch size, or we can keep it separate from DP, and we just say that EP also shards the patch size, which means that we're going to need to update the data loader to take into account to the expert parallelism process groups. And I think while I'm explaining this, some people, because this is the way we do it in Nanotron, probably some people who come from other libraries see things differently. But yeah, I think it's interesting how everyone treats this question of distributed training. But for us, this is the way we see it. And I think it's a very cool way to see it. Why? Because it enables us to add more parallelisms easier. Every axis is responsible for a different type of communication. The data loader has information of all the axes, and we can adapt it accordingly, etc. So yeah, I just wanted to explain this the notion of different axes. But then to summarize, so DP, as we've seen, it shards along the batch dimension. TP shards along hidden dimension. Sequence parallelism, that's coupled with TP, and context parallelism, they shard along sequence dimension. PP along the model layers, and expert parallelisms along the model experts. We can add vocab, which shards along vocab, loss, which is also along the embedding, the LM head, etc. And so a nice comparison to be made is PP versus 03. So what are the pros and cons here? So in 03, what does each compute unit stores? So in 03, we only have a fraction of a layer, whereas in PP, we have the full layer. The communication is used in 03, we communicate weights, but in PP, we only communicate activations. So PP is actually very light on activations, which is why some people prefer it when 03 reaches the limit, we move on to PP. Because PP is very light on communication, like we're only communicating activations, but 03, we need to communicate the entire model, all the weights. But the orchestration, both of them are model agnostic. Like you don't need to do any change in your code, more or less, because in PP you only say that these layers belong to this GPU, these layers belong to the GPU, etc. In 03 as well, you're just gonna say that the parameters of these layers are going to be sharded along these GPUs. So you don't actually need to change the code. Unlike CP, EP, and TP, you need to do some fixes. Or for example, for MLA, it's not very easy to make it work with CP and TP, for example. Implementation challenges. So yeah, what is both of them? They have their complexities. For 03, you need to handle the model partitioning and the communications and the checkpointing as well. So for pipeline parallelism, it's really complex to handle the PP schedules. You've seen the dual pipe. It's good luck implementing that. The scaling considerations. So for 03, prefer large micro batch size. Why? In order to overlap better the compute with the communication. So either micro batch size or sequence length. The idea is if you have a lot of inputs, you can do a lot of compute, which would enable you to hide the communication of the weights. In PP, you're going to prefer a large GAS, gradient synchronization steps, in order to hide the bubble. And here you can find a summary. So we've seen 03 versus PP. These are the main considerations. Now it's interesting to see how TP, CP, EP work, so that at the end we can take a look at the 5D parallelism schema. So this is just going to be a review of what we've seen earlier. So for TP and SP, so tensor and sequence parallelism. So quick definitions. So here we have the batch size sequence length here, and here we have the hidden dimension. This is a single layer, transformer layer. These are the activations, and I have my weights. So starting with the self-attention, I'm going to have the QKV projection and the out projection. So my activations here, they should be sharded. It's a small typo here, need to be fixed. So in TP and SP, my activations are already sharded. I'm going to multiply them by QKV proj. So since this is TP, my linears are sharded. So this is a column linear. So it's going to shard my inputs along H, but I'm going to keep the same batch and sequence. So I have full batch and sequence. H is sharded. Self-attention doesn't do anything in TP. And then there is out projection that requires a reduce scatter. It requires just a reduce for correctness. So I'm going to do reduce in order to compute the correct outputs. And then I'm going to scatter along the sequence dimension, which is why here the sequence is sharded and the hidden dimension is restored. It's full again. SP domain layer norm. So layer norm needs the full H. So it's good. And I still have the full H. When I enter the TP domain again, I'm going to need the full sequence, batch and sequence. So here I'm going to do a reduced scatter for this feed forward. Okay, this should be an all gather, sorry. So all gather, this is another typo. I'm going to do an all gather in order to restore my sequence, batch and sequence. And I'm going to multiply it by the feed forward in order to shard the H. This is a column linear, so it's going to shard the H. I'm going to have B8, B and S, and then I'm going to have another row linear here. The row linear here is going to, with the reduced scatter, is going to restore H, and the scatter here is going to shard along S, etc. And then there's another all gather to restore S, etc. So we can see here that we need 4 communication, 2 all gathers, and 2 reduced scatters for each layer, which is why in the cheat sheet we had like num layers times 4. And this is only for the forward. So the backward is the same thing. All gather becomes a reduced scatter, and the reduced scatter becomes all gather. We talked about it in the blog. Feel free to check it out. And so this is TP and SP. For CP, which is the context parallel, I'm gonna parallelize the work done in the self-attention. So here I have a sharded tensor. So what is sharded exactly? It's S, it should be S. So sequence is sharded along CP. Every GPU takes a different sequence. And the magic of CP is that even with sharded sequences, like even with different sequences on different GPUs, attention still works thanks to ring attention. Here I put all gather, but I could have put the all to all, depends on the implementation. But yeah, this is ring attention. And this is the only thing that changes. So context parallel only works on this self-attention and everything stays the same. This is another typo. This should be, so S is always sharded across CP. And expert parallelism means the experts are sharded across EP. So yeah, so self-attention is the same. And as I said, EP means I'm gonna have different batches in different GPUs. Each GPU is gonna have a different batch. Once I reach the router, I can reroute my tokens to different GPUs. Each GPU has different experts, so we're gonna do the calculations here, and then I need to decode, and then I need to combine to get back, etc. Yeah, and then, so yeah, EP only functions on the expert part. And when we combine everything, this is the final schema that we get. I hope you can read it clearly. So we have in blue TP, and the TP does reduce scatter, all gather, all gather. There is an all gather here that was transformed to all. So when we mix TP and EP in here in the SP domain, we don't need to all gather the sequence, because in the SP domain, the sequence is already sharded. We don't need to all gather the sequence because the router is going to reroute stuff. So it's the same operation. It can be all to all here. Yeah, so all gather here of TP is transformed to all. CP works on the attention. So here it's an all gather for ring attention. EP functions on the expert layers or the experts. So we need an all to all here and all to all here. PP, it's to send the activations between the different GPUs. So let's say first GPU has 4 layers. At the end of the 4 layers, I need to send the activations. So this is a send activation. And in the middle of the pipeline, I'm going to receive gradients as well, because usually forward and backward are overlapped. So I'm going to send activation and receive gradients at the same time. So both in and out of the layer. It doesn't have to be one layer, it can be multiple layers. So this is just for the sake of simplicity. FSDP, in FSDP, I need to all gather. So this is prefetching. So I'm gonna all gather the layer I plus 1 while I'm doing compute of layer I. And as I said, this is also for the sake of complicity. All gather can be done on multiple layers in order to all gather multiple layers in advance, etc. Yeah, and here we added some notes. For example, yeah, all gather is the only one that is a circle. Why? Because it's the only communication that moves parameters. So imagine if you have a very big model. So these all gathers will need to communicate all the parameters in that big model, whereas the other communications, they only communicate on activations or gradients in the case of backward, or both. I think I explained everything. Yeah, note CP and EP are in different dimensions. Yeah, we already explained that. So we have different axes. And yeah, so for the here we have the dimension and which dimension is sharded along which parallelism. For example, we've seen the DP shards batch. So I'm gonna have my batch that is divided by both TP and EP. And I'm going to have my sequence that is divided by CP, and my hidden state that is full. Once I'm inside the TP domain, I have my H that is divided by TP. And that's it. Why? Because the column linear is going to divide it here. So here I'm going to have parameter that is divided by TP because it's a column linear. In here, self-attention, so parameter over TP, nothing changes. CP doesn't actually shard the weights of the attention, as we've seen earlier. It only handles the sequence. So the sequences are sharded, but the QKV projection and other projection do not depend on CP. So yeah, we have param over TP, and after this, it's the same. And then out projects param over TP, and this is a row linear. So afterwards, I'm gonna restore my H. So here I have H, but I'm gonna scatter along S. So S becomes CP times TP, and B is the same. Layer norm is not sharded, it's the same. B, S, H, the same. Actually, yeah, layer norm it's not sharded, but it requires this thing. I think we made a note for this. Since layer norm, it sees different inputs on different GPUs, then it requires an all reduce for the gradients. I think we made this note somewhere anyway. And then once we enter the EP domain, I have my router, which has an all-to-all communication, and it needs to do the B over DP times EP. It needs to reroute my tokens. So it can either shard S or B. In here, it's basically depends on the number of tokens routed. My linears are sharded on both EP and TP. Sorry, 1 second. And I have my feed-forward experts I. Here, so this is a column linear, this is a row linear, so it's the same H divided by TP, and then row linear restores H and requires a reduced scatter, and then I need to all to get back to my previous dimension. And here inside this, it's similar as MLP, so H is divided by TP, S is restored. And all, this SP domain is the same as this SP domain. And then I start all gathering for the next layer, P2P and all gather. And that's, and finally, there is the memory usage and how each form of parallelism affects like the memory usage for the different forms of parallelisms. We can see that, for example, for the 8 billion model, with no parallelism, we require this much of memory usage. For TP8, with 0.3, with selective recompute, we can see that everything is sharded. So model parameters, gradients at optimizer states. The activations are not very much sharded, which is they only become sharded when we do full recompute. For TP, it's the same thing for model, but the activations are even more sharded, because we've seen that earlier. When we do TP and SP, we shard activations better. PP is kind of the same as DP, but it also depends on the pipeline partitioning. So whereas DP can perfectly partition all the weights perfectly, pipeline can only partition like by layers or something. And sometimes, for example, let's say you have 100 GPUs, you only have 32 layers. You're going to need to make you need to find a good partitioning for that over your PPGPUs. Context parallel when CP is 8. So yeah, it's only the activations that are sharded. CP does not shard the model, and expert parallel only shards some linears, which are the experts, only shards the experts of the model, and doesn't shard the activations. And I think this summarizes everything. We made some table here with our final finding, and then we can finally go back to so the cheat sheet. It's basically what we talked. So we start with TP. Once we scale too much, 512, we need to combine at least 2 forms of parallelism. If you have very long sequences, you want context parallelism is the most efficient in attention. If you have mixture of experts, you want to use expert parallelism. In case you want to save up more memory, you can do full activation recomputation or gradient accumulation, which would enable you to reduce the micro batch size. Then you try to achieve the target global batch size. For this, either you scale up the data parallelism or gradient accumulation steps. For long sequences, you can scale up CP, because when you scale CP, you're going to scale the sequences, and vice versa. And then to optimize training throughput, try to find better trade-offs between the different forms of parallelisms, depending on the size of your model. So TP, you try to keep it within a single node. For DP, you try to not blow up your target batch size and keep it, depending on your network, below 512 GPUs. And when it becomes a bottleneck, you can add PP as well. And then try to experiment with micro batch size for better balance between global batch size, model size, compute, and communication. And these are the final results we found from our experiments. We can see as we scale the model size, let's start with the smaller model size. As we scale the number of nodes, which means the number of GPUs used, so for the smaller model size, scaling the number of nodes means a lot of communication or a very heavy partitioning. So a lot of communication, but not a lot of compute, because the model is so small, there is no compute to be made. So we reach a very bad MFU here. And so, in general, there is a sweet spot that is in this diagonal between the model size and the number of nodes that needs to be respected. So sometimes PP is the best, sometimes TP is the best. It depends on the network, the implementation stuff. But usually you're gonna find the best MFU. So you're gonna use the best efficiency for your global batch size, for your model size, and depending on how many GPUs are available. For example, if you have 80 billion parameter models, you need somewhat 16 nodes. Each node has 8 GPUs in order for it to be efficient. And we have some lessons learned on benchmarking. Maybe you can do another blog, or maybe I'm going to summarize that in a tweet later on. So stay tuned, because I think it's very interesting to explain the lessons we learned in our benchmarks. And that's about it for parallelism. And the final remark, I think it's one of the most important ones. Basically, we were making the assumption that computation and communication can be effectively overlapped, but the reality it's not as perfect as explained in this blog post. Yeah, in reality, once you start overlapping, you have some contention between communication and communication. So yeah, you can read more about this in this blog. That's about it. I don't know if there are some questions.
Sweet, yeah. Congratulations to people who made it this far. Yeah, I guess like if folks have any questions to Nouamane, like I guess like we can hang out like for another few minutes. I see the first question is by Calvin, which is, did you guys use Unsloth? Did you use the graded accumulation bug fix in your experiments?
I'm not familiar with that gradient accumulation bug fix. Yeah, no, we didn't.
I suspect if you're using like the Hugging Face, you're probably not using the Hugging Face trainers, right? This Nanotron is its own code base.
Yeah. No, we're using Nanotron only in the experiments. And Nanotron builds upon PyTorch and transformers only.
Got it. I guess like another question is from Akeem, which is like basically, yeah, like what are you thinking about doing next now?
Yeah, well, DeepSeek has given us a lot of treats to explore. So I think next is diving a bit down into the collective operations and see how we can like boost the performance better. Also, like make the Nanotron library easier for people to contribute to and work with, because yeah, it's hard to maintain the documentation stuff. So there is still some work to be done there as well.
Sweet. I guess I have an important question. Are you guys going to open up the physical books more? Because I really wanted mine as well.
Yep, and that's coming up soon.
Excellent.
Yeah, I don't really have a date in mind, but yeah, expect some physical books soon of this blog.
Excellent. All right. Well, I guess I don't see any more questions in chat, but Eddie pointed out that you can actually also open up questions on the discussion on the book directly if you have any feedback or questions. Yeah, on the community tab right here. Otherwise, like Nouamane's like pretty active on Twitter as well, so feel free to message him directly or tweet at him if you have any clarifying questions. Yes, and we'll repost this link on Discord. And if more of the Ultra Scale team wants to hang out there, we'd love to have you guys help people out. Otherwise, yeah, I guess like Nouamane broke the record, so I think the record is now 3 hours and 10 minutes for talks on the server. The previous one was on Tensor Cores, which is 2.5 hours. So like I think this is I doubt anyone will sort of exceed it anytime soon. So yeah, we're meeting again tomorrow to talk about like low bit kernels for metal. So if you're interested in a very low scale, like just your laptop, it can be a very different kind of talk. But we hope to see you. And I agree with Eddie that like I think Nouamane is probably one of the goats in the field. So thank you. This was very, very comprehensive. I think you made me really want to go and dive back into the book as well to sort of go over like all your charts. I think especially near the end it got like really meaty, and so I kind of want to sort of slowly read all that with a cup of coffee.
Yeah, and thank you so much for sticking through all of it. Sorry for making you sticking through all of it. Yeah, you can imagine, yeah, just how much time it took to read and stuff. And we're very happy to share everything like in this simple blog. And hopefully we're hoping that through such works, we push more people to learn about these parallelisms, contribute, try out things, and not only wait for like big big tech companies to launch new models to use them or just fine tune them and stuff like that.
I think the internet is stronger together. I agree.
Exactly. Yeah.
All right, Nouamane. It's an absolute pleasure. Thanks again, folks, and we'll see everyone tomorrow. Bye-bye.
Thank you so much. Bye.